We're going to resume with Leonardo Cruz. Leonardo is with Equinor and a extensive user or avid user of ResFrac. He's also an avid cyclist, which of course is close to my heart. And I'll leave it up to him to divulge at what speed he was going when he broke his ankle. But he recently suffered a bad ankle break from cycling, but was just speaking with him the other day, and he's back to like riding 70 to 100 miles. So congrats, Leonardo. You're embodying the best of us.
Yeah, I was biking at about 1 mile per hour, something like that. So, not very good.
Like I said,
anyway.
You whether you decided to do that.
Yeah. Well, thank you very much for the invitation. So the title of this presentation is PinPoint versus multi-cluster completions and well performance. First, I'd like to acknowledge my co-authors from the Equinor Research and Technology Shale Oil and Gas team, Avi Kulkarni, who I think is here, and the guys probably here too, he's listening, and Jason Bryant. Who did all the heavy lifting, analyzing all the data, including all the operational considerations, and also creating an early version of this presentation. So I was mostly involved on the, I'm actually contribute to the geomechanics aspect and the stimulation and hydraulic fracture and completion modeling part of this study. I should also add that the results of this study are not necessarily aligned with our asset current operational plan or development strategy. But since we are a research group, we like to consider alternative approaches that could potentially improve the profitability and also be added as a tool in the technology toolbox. So this is the outline of the presentation. We have structured this relatively quick presentation to first address why we are talking about this again. Then we'll discuss cluster level analysis and other considerations such as stimulation and production mechanisms. Then an interesting case study from a liquid-rich basin. We do have more examples, but we are only showing or focusing on one example for this presentation. Then a more detailed analysis of what modeling has to say for this case. And finally, some closing statements. So please, we encourage you to think of questions for anything you'd like to have clarified or to extend our perspective on the topic, or just simply filling some gaps together here. So I will just go very quickly to explain this with these simple cartoons or drawings, what these two technologies are. So basically, plug and perf on the left is the stimulation method that uses wireline perforating guns and plugs. So the assembly is pumped down the horizontal section where the plug is set, and then multiple perforations clusters are shot at a specific depth before pulling the assembly out of the well. In contrast, PinPoint completions on the right perform a stimulation through single point of entry to create more control, or presumably more control discrete fractures. Historically, these have been performed on one of two ways, either with coil tubing fracturing through hydrojet perforations or coil tubing manipulated sleeve, or with the ball drop sleeve with open hole packer isolation. So now let's take a step back. For years, this debate considered all the pros and cons, such as efficiency, open hole versus cemented, stimulation production, cost, risk, or just pure preference one way or the other. Then cement isolation became mainstream, and plug and perf completions got intense and efficient, basically making good wells. Then the slip technology struggled to keep up with all that. The relevant studies at the time were only able to compare, for example, a 40-stage slip job to a 120 plus cluster plug and perf job, far from comparing apples to apples. So rather than the debate being empirically settled, the scale just sort of broke, leaving slip innovators scrambling for solutions. But actually, that didn't stop innovation in a way. So in the sleep technologies for the past few years, there is a convergence occurring where the system performance, cost, and operational risk are getting closer to making this a real consideration. There have been failures in the past, and we know most of the operators have suffered from those. But the fact are now that basically more recent technology or more recent jobs have completed high stage counts. For example, 200 plus per well, with systems that are fully cementable, interventionless, and so forth. So these technologies may help answer big challenges with our marginal acreage, searching for new solutions that can help to optimize the strategy of drainage and make those projects presumably more economic. So the goal of this section that I will show is to present a case study on PinPoint and plug and perf and try to generate some healthy discussion on whether this PinPoint technology is relevant in 2020 and beyond for these unconventional fields. For this, it is important to understand how we are stimulating the rock at the individual cluster level using these two methods. Key stimulation parameters like rate per cluster, proppant and fluid per clusters are directly related to fracture length and fracture conductivity, and therefore production per cluster. It is very well recognized that PinPoint systems enable higher rates going into each fracture, improving proppant transport within these fractures. Also, I should mention that the case study that I'm going to discuss was performed in 2016 using previous generation of equipment. So we have limited number of fracture per stage because of the technology. Since then, the PinPoint system have really advanced and we can achieve more number of stages. So these results at cluster level form the basis of the discussion and extrapolating high number of fractures. So now to the case study. This is a 4-well pad with no producers and fracturing activity in the vicinity. The wells 2 and 4 were completed using plug and perf, basically 5 clusters per stage. Well 1 was completed using single entry PinPoint fracturing, assisted with coil tubing sleeve, whereas well 3 was completed using partial sleeve and also partial plug and perf. So wells 1 and 4 are both unbounded on one side, and hence they are ideal for comparison purposes. We use hybrid fluid system with 30-50 white sand for all wells. So you see the fracture spacing is almost the same, and so is the proppant intensity per cluster. Major difference, single entry in well 1 versus limited entry in well 4. and much higher rate per cluster in well 1, as we discussed. So therefore, this is one of the actually most apple-to-apple case study we have seen in recent times, at least from us internally, to compare PinPoint and plug-and-pair fracturing. Here with some results. So we have more than 3 years of production history. The gas lift was installed on both wells within the first 6 months. So this graph shows the cumulative oil production normalized with lateral length. So as you can see, the PinPoint well 1, which is in blue, clearly outperformed the plug-and-pair well number 4. The table on the right shows both the cumulative oil production with lateral length and also normalized per fracture, assuming for the plug-and-pair 100, 90, and 80% efficiency, just for reference. So we all know that it can be misleading to just look at production rate. So we have used rate and pressure data to perform RTA, rate transient analysis. So the graph in the lower left shows the inverse PI plot, meaning the rate normalized pressure versus superposition time. So lower the value of PI, better the stimulation quality and well productivity. So as you can see, well 1 has better performance over the longer duration. From the slope of the inverse PI plot, so you can estimate a parameter called A root K, which is an indication of fracture length and the stimulated matrix permeability. So this bottom plot shows the normalized A root K with lateral length and with normalized per fract as well, showing that PinPoint well, or the PinPoint well, has a superior stimulation quality than the plug-and-pair wells. So overall, this was a very conclusive case, at least for us, that shows at cluster level, PinPoint fracturing is far superior. So based on the previous field data and other field data that we are not presenting here because of time mainly, we decided to design some single stage completion models using ResFrac to try to understand why we are seeing this behavior. So 2 modeling cases were considered. Case 1 is PinPoint, case 2 plug-and-pair. So as a background, the 1D geomechanical model is based on data from the actual field case that we just saw. But we're using unconstrained reservoir parameters in this presentation. So no attempt to perform a detailed history matching is shown here. But the intention is rather to try to understand the potential mechanisms that are operating during stimulation. So some of the completion details are shown in this figure. On the PinPoint side, so we have 9 slip, 2 cases for rates 20 barrels per minute and 80. So we're trying to go to the extreme end members. On the plug-and-pair side, 9 clusters, also rates of 80 barrels per minute. So the total volume pump in the 9th fracture is exactly the same for the 2 cases. So the main difference is that a PinPoint, the cluster are pumped 1 by 1, but in the plug-and-pair, the fractures are propagated simultaneously. So we're assuming stage fracture from the toe. So there is no stretch shadow or pre-existing stretch shadow. So it's like a virgin reservoir. So what we're trying to address here is fracture control. So is a control over the size, geometry of each fracture an issue at all when it comes to completion design? On the PinPoint side, some people said that basically it provides very consistent and repeatable fracture placement in the well and also from well to well. And in the plug-and-pair side, some people say that it's extremely challenging to accurately and equally frac each zone. Well, the idea is to, with this study, to check the reservoir geomechanics modeling perspective. So in the figure, I show here two pressure fields after 1 hour of pumping for these two cases. You can see that over time, the two experiments evolve very differently. And you will see more details in the next few slides. Here, just to show the pumping schedule and volumes. So in the PinPoint case on the left, fractures were initiated every 30 minutes, whereas in the plug and perf case on the right, all the fractures were stimulated at the same time. And again, the same total volume and proppant mass was pumped for the two cases. Just a bit of technical background. I guess most people is aware of this, but so the main physical process operating under these conditions are stress shadow and the time-dependent poroelastic effect. Just a little bit of background. The graph on the left shows the analytical solution for stress variation perpendicular to a crack. It's a 3D crack. It's a homogeneous, isotropic, and linear elastic formation. So when you inflate the fracture, there is internal pressure, and you induce very large stresses. So the largest stress is in the compressive, is a compressive stress that is normal to the crack. Then the stress perturbation in the direction of the fracture is small, is a blue. The blue line, and there is some tensile in the vertical direction. So it's the green dots below and at some distance. So the graph on the right shows a ResFrac simulation of a single crack and the corresponding stress field. So there are additional questions like, is the increased stress shadow equal to more complexity? There is also the debate about the secondary parallel fractures or the shear fractures and how they operate or both. Well, we are staying away from it in this presentation, but however, we are considering aspects of it. For example, by using the pressure-dependent permeability feature in ResFrac. So we are assuming implicit discontinuities that serve as leak off and also affect the pressure. So we are not modeling explicitly this complexity or these discontinuities associated with the complexity, simply because it's not practical to actually model all of them. So as we thought during the day, this complexity aspect may be basin specific. So in some situation, production may benefit from longer but uncomplex fractures, but in others, shorter fracture with complexity around it may be more relevant. So this is a very different discussion that will not be addressed here. Now I will show 3 animations of the cases. This is an animation showing basically the PinPoint case at 80 barrels per minute. You can see the sequencing of the PinPoint fracturing and the fracture distribution here for reference. The lower left animation is basically the aperture over time. As a comparison, I guess this one, this is the animation that shows the PinPoint case, but at 20 barrels per minute. You can see that there are some differences in the total fracture surface area, just visually, compared to the previous case. You can also see that the system becomes kind of unstable, showing some fracture asymmetry at the end of the, I think it's the last two fracture or sleeves. Then this is an animation for the plug and perf case at 80 barrels per minute. You can see here the fracture propagating simultaneously and showing an increased asymmetry. So here is again is the aperture on the left that I didn't show the propan placement, but this is after basically 3 years, and you can see where basically the propan is. So if we compare PinPoint versus plug and perf, for example, with the 80 barrels per minute cases, we see the fracture geometry in PinPoint is symmetric or more symmetric relatively, is biwind, and propan is more evenly distributed. In this case, the aperture. The fracture geometry in plug and perf is asymmetric. Definitely is no biwind, and propan is unevenly distributed. So this is a view from the side of the well bore parallel to the fractures. And you see that PinPoint fractures are more or less staying at the same depth, the same interval, or in zone. But on the right, plug and perf fractures move up and down. So in some cases, this may or may not actually affect the producibility if you are actually getting out of the zone. This is a total surface area and total prop area for the two cases. And we can see here it's a prop area, and also the surface area is larger in PinPoint, which is the segmented line, versus the plug and perf, which is the continuous line. So there is a difference in some cases of up to 40% in the surface area. This is a cumulative hydrocarbon production, which is larger, and now it is about 10% larger in PinPoint than in plug and perf, and significantly larger cumulative water production as well. So they have some implications on what type of behavior between the actual clusters is going on and governing the permeability and the water saturations and so forth. So to summarize the model study, fractures appeared less symmetric in plug and perf than in PinPoint. Specifically for plug and perf, external fractures are relatively larger than the internal fractures, and the fractures fluctuate up and down as a result of the stress shadow. Surface area and prop area are larger for the PinPoint, 40%. Cumulative hydrocarbon production is larger, about 10% in PinPoint than plug and perf. And the main difference in the evolution of the model seems to be the stress shadow and the way the fractures avoid each other over time, and the resultant fluid and propan distribution. So far, we presented the case or this study and modeling result. Now we want to dedicate some time to look at kind of the broader picture of completions and well spacing optimization. First, let's understand how the completion design has evolved over the last 5 years. So we have gone from hybrid fluid system and large mesh propan to slick water fluid and finer mesh propan. So the fluid and propan intensity increased, but has been kind of stagnant in the last 2 years, since 2018, as operators are going into a more factory mode. So most significantly, the cluster spacing has reduced from average 40 to 60 to 15 to 20 feet in the plug and perf. So this is why the debate has shifted to plug and perf fracturing mostly. So in order to kind of rejuvenate the debate, we ask.
Obviously, the first step is to move to develop by half section instead of third.
I can see some people talking or questions.
That's kind of the green boxes here, and the green fairway shown.
So what drives the cluster spacing? Is it the reservoir permeability or the accelerated production? So our observations is that in most unconventional plays, irrespective of the permeability, operators have downspaced the cluster, which means that it's likely accelerated production. Are we sacrificing the frac quality Is it compensated by adding more wells? Do we need ultra tight cluster fracture spacing of 15, 20 feet? What is the optimal cluster spacing? So I'd like to wrap up with conclusions and recommendations. This case study demonstrates superior performance of PinPoint fractures, helping to uplift recovery per frac or per cluster. The modern PinPoint system that enables 200 to 300 stages could provide a realistic opportunity to increase EOR per well. And the industry needs to continue to address operational and cost challenges of PinPoint system and capture lessons learned. That's very important to document successes and failure. So I'm open to questions, so I open up for any follow-ups as well.
Great. Leonardo, thank you so much. Very good presentation and well received. We'll just limit to a couple questions just to ensure we remain on schedule here. But there is a question on relative completion costs. I'm not sure if you can divulge that or not, or give some sort of indication on how you would approach that NPV analysis.
Yeah, I mean, we have done some economic analysis, and so we are getting close. So if you, for example, choose sleep every 40 feet or 50, maybe you are, kind of comparable to plug and perf. If you go lower, it may not be. But I mean, the whole idea is that since the technology has been improving, costs have been going down. So we are getting to, to that convergence where we can, almost get a similar cost when you compare PinPoint versus multi-cluster completion. So.